Okay, good evening. Right, so let's continue our discussion on maths. Okay, so still we are in the topic one. So remember, topic one is the biggest topic anyway. So last time we discussed start discussion on matrices. So let's try to finish it today. So then we need to. I just use the old note because it's more organized, more detailed. Let's try to finish that discussion so that we can move on to the some additional contents in your new note as well, okay? Because new note is much more uh, compact at the same time. The syllabus is bigger, okay? Because this is semester three maths. I'm using semester three math syllabus note, previous use. Now it's finally a maths, therefore it's more abstract, okay? Right. So I told you matrix is no boring topic, but anyway, it's very important for data science, AI, and so many other places, okay? Especially computing. Right. So we start discussing matrices last time. So matrix is arrangement of numbers in rows and columns format. Why are we interested? Because there are so many representations, especially solving equations. We can represent our especially linear equations like we used to call them simultaneous equations, samagami samekami, and then solve those equations because the things get more complicated when we have more than two variables. Of course, if it is just two, three, four, it's not issue. But about if we want to extend that concept into n variables, right? So that is the reality, right? So we discussed that every matrix has a size or order. Individual items are called elements. We discussed some special matrices like row matrix, column matrix, square matrix, diagonal matrix, zero matrix or the null matrix. Remember, some of these special matrices are square matrices. Some of these are not necessarily square matrices. For example, null matrix can be any matrix, whereas diagonal matrix must be first a square matrix and then all the non-diagonal elements must be zero. Right? Symmetric matrix, again, a special case of a square matrix where Aij is equal to minus Aji. Okay. Symmetric matrix Aij is equal to Aji, whereas skew symmetric Aij equal minus Aji and Aii is zero. So then upper triangular matrix where lower triangular values are zero, lower triangular matrix where all the upper triangular values are zero. Identity matrix, it is again a special case of square matrix where all the diagonal elements are or Aii where Aij where I equal j is 1 and Aij where I is not equal to j is 0. So you need to explain it in a very precise manner. So then we discuss what is mean by two matrices are equal. First of all, the order must be the same, the size, and then each and every individual elements must be identical. With Aij equal Bij for each all I and j. So then we discuss how to add two matrices. Only matrices of same order can be added. And basically we add the individual corresponding elements. Aij plus Bij is Cij. Likewise, you need to explain it in a very abstract manner. That is good for your abstract thinking, right? Your communication. Because software developers, our main task is communication. Writing a program is communicate our solution to the computer. Right? So when we communicate something to the computer, it must be very precise. So therefore sometimes students don't understand the value of maths. So maths is the language of science. So when you're good at maths, basically one aspect is you're very good at abstract level communication. That is why your syllabus is heavily abstract, right? Heavily abstract concepts. Okay. Sometimes you find it's very difficult to understand because it's so abstract. So abstract thinking is super important. Right. So then we discuss the scalar multiplication. Again, you can't just multiply any two matrices. So you can multiply two matrices if number of rows in the first matrix is same as number of columns in the same matrix, second matrix. Okay. Uh, and we multiply rows, first row with first column, first row with second column, and so on to get the resulting matrix. Okay. Of course, this is the multiplication by scalar. Then you just multiply each and every element by that scalar. So that is called scalar multiplication. And from that, we discuss subtraction also. Subtraction is first matrix plus minus 1 into the second matrix, add it. Okay, so basically that means you subtract individual elements. So we look at some properties of scalar multiplication. Yeah, then we move on to the matrix multiplication. Okay. So remember 1 into 1 plus 2 into 2, that is your 1, 1. Then 1 into minus 1 plus 2 into 0, that is your 1, 2, and so on. So if this is 2, 2, and 2, 3, what you get is 2, 3. So this must be the, so number of, first we have the rows, then columns, number of uh, columns must be same as number of rows. Number of columns, sorry, I made a mistake earlier. Number of columns in the first matrix must be same as number of rows in the second matrix. Then only you can multiply. How to multiply? You take a first row and with first column, that is this. First row with second column, that is this. First row with third column, that is this. And then second row with first column, that is this. Second row with second column, this. Second row with third column, this. Okay. 3 into 0 plus 4 into 1. I think that is where we stopped. No, we did discuss few more things. Right. So then the transpose of matrix is simple concept. So basically, just try to explain it abstract manner. So if you have A, again, this is for any matrix. This is not only for square matrix. Say Aij, M by N. Then what is transpose? Transpose, A transpose is uh, Bji, or we can say B, Bij equal Aji. So that means your row become column, column become row. And for example, your 2, 3 item will become 3, 2 item. But 1, 1, 2, 2, 3, 3, 4, 4 items will be the same. Right? So that is the abstract explanation. But by looking at it, you can do it also. 1, 2, 3, 4, 5, 6 will be, its transpose will be 1, 2, 3, 4, 5, 6. Now this is 1, 3 element will become 3, 1 element. 1, 2 element become 2, 1 element. Right? 2, 2 element is still 2, 2 element. 2, 3 element is 2, 3 element is 3, 2 element. Okay, so that is called transpose. And we look at some special features of transpose matrix. A plus B transpose is A transpose plus B transpose. That is common sense. A transpose of a transpose, you are getting the same. That is very common sense because you row become column, column become row, and again you change it. Again, your row is row, column is column. And this is an interesting property which is not very straightforward. When we have AB transpose, which is same as B transpose A transpose. Of course, that is if A and B are multiplicable. Right? So remember, this is not A transpose, B transpose, B transpose, A transpose. And finally, we look at what is orthogonal matrix is. That is, if matrix multiplied by transpose matrix, if we get identity matrix, that is, in other words, matrices inverse is its transpose, then we call that orthogonal matrix. But still, I did not explain how to how to find inverse matrices, but Just I gave you the definition. If I have a matrix A, if I can find another matrix B such that when you multiply, you get an identity matrix, then this is the inverse of this matrix. And if that is the transpose of this one, then we say this matrix is orthogonal matrix. Okay, that is very, very special case. Okay, right. Uh, so inversions we will discuss after discussing the determinants. Okay, right. So therefore, let's finish our discussion on determinants and then we'll come back to inverse matrices. Okay, right. So now we'll start our today's session. The first subtopic is determinant. Right. So determinant is a property of a matrix. Not every matrix has a determinant. Again, determinant is there for square matrices only. So I told you whenever you learn a concept, just double check whether is it general concept or only applicable to square matrices. So determinant is a special property of a value that we can calculate for square matrix. So that means every square matrix has a determinant. Determinant is a number. Right? Determinant is something like a 5, -3, 0. So we can calculate the determinant of any square matrix. Right? And we represent, if my matrix is A, as a notation, we either you can say determinant of A, or you can just something like absolute value. But it's not absolute value. We use the same notation. Okay? Right. Uh, so why are we interested in determinant? There are some properties, especially when we do calculations related to inverse matrices and so on. So this determinant is very helpful sometimes to calculate, sometimes you just check whether it has a inverse matrix and so on. Okay, so therefore this number is very important uh, value for a given square matrix. Right, so how to calculate the determinants? So if it is one by one matrix like this, just you have one data. Its determinant is that data, that value itself. So therefore determinant of A is again 5. If the only element is -3, the determinant is also -3. Okay. So this is just a definition. Okay. Definition. So then if you have 2 by 2 square matrix, order 2. So how to find the determinant? So you cross multiply your diagonal elements, subtract as cross multiplying your other diagonal element. This is your main diagonal element. Then subtract the other diagonal element after multiplication. So therefore, it's A11 into A22 minus A12 into A21. And you get a number. Okay. For example, if your matrix is this 2 by 2, 5 into -3, -15, minus 2 into 1, that is -30, -15 minus 2, 2 -17. So therefore, determinant of this matrix is -17. Okay. So this is just a definition uh, because this number is very useful later on. Right. So what about if you have order 3, 3 by 3? Now things are getting a little bit more complicated. Right. Again, let's Aij be a square matrix of order 3 or 3 by 3. Uh, so how do you calculate the determinant? So there's a way to do that. Okay. So you can take any row or any column. Right? You can take any row or any column and calculate the determinant. This is how you do it. So let's assume we use the first row. So then take the first element. When you take the first element, then shade the row and column related to that and find the determinant of the other square matrix. So then you get a smaller square matrix. So that, of course, if it is, of course, it's 2 by 2, this multiplication that is A22, A33 minus A23, A32. Okay. So then minus second element into, when you remove the corresponding row and column, So now I'm interested in this one. So then remove these two. So then you get A21, A23, A31, A3. You get a matrix like this. A31, A33. Now you need to find the determinant of this one. Okay. Multiply value of element by the determinant of this matrix, which you can multiply, cross multiply and get it. So then take the third one, and now you need to shade, because you are interested in this one, these two, you get another square matrix, find the determinant of that one. You can say this is positive, this is negative, this is positive. Positive, negative, positive. So how do you determine whether it's negative or positive? It is basically when you add these elements. So this is 1, 1. 1 plus 1 is 2. If it is even, positive. 2 plus 1 is 3. If it is odd, it is negative. Again, 3 plus 1 is 4, positive. Or we say minus 1 to the power I plus j. If I plus j is odd, it is negative because minus 1 to the power odd power is minus 1. And if I plus j is positive, even, like 3 plus 1, 1 plus 1, so then minus 1 to the power 4, minus 1 to the power 2 is plus 1. So because we need a mathematical definition. So that is how this become plus minus, always plus. So if first one is plus, for example, this is the minus because odd. If because you can take any row, any column, any column and calculate this. For example, if you take second row, so then A21 into, when you shade this and this, the determinant of this one. But this is negative. Negative A21 into M21. Because 2 plus 1 is 3. Then this is 2 plus 2 is positive. A22 into M22. Then this is again negative. A23 into M23. What is M23? When you shade these two, you get a 2 by 2 square matrix. It's determined. And finally, what you get is a number. And that is the determinant of that 3 by 3 matrix. Okay. So this is not difficult at all. What we are doing right now is not at all difficult. Only thing is you need bit of patience, you need bit of abstract thinking to, especially you need to check whether can I explain it back? Can I write the definition in a very compact manner? Because at the end, mostly for you guys, uh, unless you go for a PhD or something or very advanced research area, the take home from the subject is your abstract thinking is better. Your communication, I mean, when I say communication, mostly when you are doing programming, because you keep communicating with your computer. And in general, your normal communication will also be better, right? Because you should be able to explain things in a very precise manner, even when you communicate with someone else, like understanding the requirement, documenting the requirement, and so on. Okay. Right. So let's calculate the determinant of this one. Remember, you can take any row, any column. Right. So let's take the third column, because you can take any row. Of course, you just take your convenient thing. Okay. So this is 1, 2, 3. This is 1, 3. 1, 3, 2, 3, 3, 3. So then how do you calculate? A13, that is 2 into, now remember 3 plus 1 is 4 even, therefore it is positive. So then you shade this. So then you get 2, 1 minus 1, 0 is determinant. Let's calculate it in the next step. So I just say this and this, 2, 1 minus 1, 0. Now I will take this one. 2 plus 3 is 5, that is negative. Odd dot means negative. Minus, so this element into, now I need to shade this and this, 1, 0 minus 1, 0. So this is 3 plus 2 is, sorry, 3 plus 3 is 6, even, positive, but this is minus 1. Now you shade these rows and column, 1, 0, 2, 1. Okay. Now we can calculate 2 times this 2 into 0 is 0 minus 1. That is plus 1. Minus 2 times 1 into 0 is 0. 0 into minus 1 is 0 minus 0. Minus 1 times 1 into 1 is 1. 1 minus 0. So that means 0 plus 1 is 1. That is 2. Minus 0 minus 0 is 0. 2 minus 2 into 0 is 0. 1 minus 0 is 1. 1 into minus 1 is minus 1. 2 minus 1 is 1. Okay. So the answer must be 1. So whether you get first row, second row, third row, first column, second column, whatever the row or column you take, so you must get the same value. Same value when you follow this logic. Okay. So that is how you calculate the determinant of size 3. Right. Any questions? So we can extend it to size 4, size 5, size 6, or any order. Of course, determinant is only for the square matrices. For example, if you are given uh, that is 3 by 3, right? 4 by 4. 0, 2, minus 1, 1, 1, 0. I'm using a lot of ones and zeros because that help you quickly calculate it, okay? 0 minus 2, 1, 3, 0, 1, 0, 0, 1, 2. Now this is a matrix of size order 4 by 4. Again, use the same concept. You take any row or any column, okay? Uh, let's say we take first row. So then this is A11, A12, A13, A14. So this is even, this is odd. This is even, even means positive. This is 4 plus 1, 5. So therefore, A11 into M11 minus A12 into M12 plus A13 into M13 minus A14 into M14. Now separately you need to calculate M11. M11 is when you, now A11 is 0. This is M11 is another matrix because you shade these two, then 0, 0, minus 2, 3, 0, minus 2, so 3, 0, 1. Remember we have shaded this, shade this one and this one. Then 0, 1, 2 minus A12, that is 2 times a determinant of, you shade this and this, 1, 0, minus 2, 1, 0, 1, 1, 1, 2, and plus A13 minus 1 times. So then you shade this and this, and again you get a 3 by 3 matrix. Then this time, again you get 3 by. Now, then you need to calculate this one. That is, you take any row and column and again calculate. It's sort of a recursive you need to calculate. Right? So you calculate somewhere else and get the value. So then 0 into that value minus 2 into this value, blah, 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 you get. It's time consuming. I told you, right? It's time consuming. Now, of course, if you are manually doing it, it's very boring because it's all about arithmetic, right? Addition, multiplication, subtraction. So that is what the boring part of matrices. Of course, once you learn it, you don't manually do it. There are plenty of software programs. Even you can write your own program to do these calculations, but you must know how to calculate it, right? When you learn, then of course you use, okay, right? So take a 4 by 4 matrix and do the calculation by yourself and see whether you get the answer. And you can double check with ChatGPT whether your answer is correct. Okay, right. So now we move on to uh, properties of determinants. I'm not going to do a lot of questions with you. You guys are in the final year. So final year is not grade 5 scholarship program. So you should do it and check with ChatGPT. And if your answer is wrong, just double check with ChatGPT or go to a tutorial and again double check what's went wrong. Okay. Right. Some properties of determinants. Right. So we are going to look at few properties. You can see quite a number of properties. Okay. Uh, so the first one is let A be a matrix of odd n. When I say odd n, square matrix, right? N by n. Otherwise, I will say m by n. Right? If someone says odd n, it's a square matrix of n by n. Or else they will say m by n if it is not a square matrix. So if you have a square matrix, the determinant of its transposition matrix, transpose matrix is the same as the determinant of the original matrix. Say this is a square matrix, and if you calculate the determinant, it's same as the determinant of its transpose matrix. Transpose matrix means your first row become first column, second row becomes second column. And this one 4 minus 6 minus 2. This one 4 minus 6 minus 2. Same answer. So that is interesting property. It works for any square matrix. A 3 by 3, 4 by 4, whatever. So if you have a square matrix, its determinant is same as its transpose matrix's determinant. Okay. So that is a property number 1. Property number 2. If you have a square matrix, of course, determinant is only applicable to square matrix. So therefore, when I discuss about a property of a matrix, determinant, it's referred to a square matrix. Right. So let A be a square matrix. Okay, this is A. And if you want to find the determinant of that matrix multiplied by a constant, K. And then you get a matrix, right? That is 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 2 into 4 is 8. In this case, we take K as 2. And if you want to find the determinant of this one, it's same as you find the determinant of this one and multiply by K to the power n. N is your order. So that means rather than you multiply these elements and find the determinant, there's another option, that is you find the determinant of this one. Then multiply it by 2 to the power 2 in this case, because this is 2 by 2. Because it's k by k. Then 2 to the power k. Sorry, this particular constant to the power this n, if it is n by n. Okay. So that of course you can double check by yourself. And of course you should be able to explain why is it so. For example, this is, if you take multiply this 2, 2 into 2, 4, 6, 8, then find the determinant. 8 into 2 is 16, 16 minus 24. Right? 16 minus 24 is minus 8. Now that is after multiplication of each element. So the other way is 2 to the power 2, that is 4, into determinant of this. 1, 2, 3, 4. 2 to the power 2 is 4. Right? So 4 into 1 is 4 minus 6. 4 minus 6 is minus 2. Minus 2 into 4 is again minus 8. You get the same answer. So either you multiply matrix by that constant and find the determinant of this one, or find the determinant of the original one, but multiply it by that constant to the power, if this is uh, n by n, 2 to the power, or k to the power n. Okay. So again, you should be able to explain why. Why do you need to, why this is going to work? If you use little bit of common sense, logical thinking, you should be able to explain why this is correct. Right? Why is it correct? Right? Just you need bit of common sense, maybe little bit of time. Right? I'm not going to explain why. Can anyone explain? If you are a logical thinker, even now you should be able to explain why this is correct. Anyone want to give a try? Anyway, I'm not going to explain the reason because if you can't explain it now, just think about it. Maybe you should be able to explain it in half an hour. But only thing is you need a bit of thinking. Maybe straight away you got it. You got it. If you can remember the definition of multiplication, because sorry, definition of determinant. Right. Anyone want to give a try? Why this is correct? So there are two challenges now. First, have you understood the logic? Have you got it? Second, can you explain it simply? So when you give an answer, that means both are fulfilled, or if you give a proper answer, reasonable answer. That means your logical thinking is good so that you can understand a particular logic, and your communication skills are good so that you can explain your solution in a very precise or reasonable manner. Right. I'm not going to explain why this is correct. I just keep it for you. Right. Maybe not, maybe after looking at this, thinking about this for another 15, 20 minutes, you will have an answer for yourself. Okay. But double check whether your answer is correct. Maybe you can double check with ChatGPT. You can give your answer to the ChatGPT and ask, is it correct? Right. So that is your second property. Right. So the first property is determinant of matrix is same as its determinant of its transpose. When you multiply a constant, k to the power n times the original determinant is the result. Right. Our next property is if you have a square matrix, obviously, because there's no determinant for non-square matrices. If any two rows or columns are same, its determinant is zero. Any two columns or any two rows. Like for example, this one, you can see the first column is 1, 2, 3, third column is 1, 2, 3. Then you don't need to calculate. You can straight away say its determinant is zero. If you calculate, you will get zero. If you calculate again, you will get zero. Right? So that is a very, because this, otherwise you calculate, right? But if you know the properties, you don't calculate because you know your subject. So one student calculate and find zero. Other students, knowing this property, know that it is zero. So first student come home and say, the time is not enough. Second student will say, no, I just managed to do it. Time is enough because you know your subject. You are efficient. Right. So let's see whether, for one example, you can take any row or any column, any row or any column. For example, I will take the second column in this case. Uh, so then 3 into, this is 2, 1. This is 2, 2. This is, sorry, this is 1, 2. 1, 2. This is 2, 2. This is 3, 2. So this is odd. 2 plus 1 is 3. That is minus 3 into, to shade this, 2, 3, 2, 3. 2, sorry, this one. Sorry, I took this one. So that is minus 3 into, when I shade this and this, 2, 3, 2, 2, 3, 3. 2, 2, 3, 3, because I have shaded this. So then this one is even plus 4 times. I shade this 1, 1, 3, 3. Then this is odd 3 plus 2, 5, minus 5. I shade this and this 1, 1, 2, 2. And clearly you can see 2 into 3 minus 2 into 3 is 0. 1 into 3 minus 1 into 3 is 0. 1 into 2 minus 1 into 2 is 0. So therefore all are zeros. Yes. And if you take any other rows, column or row, so you will get the same results. Any row, any column. I just took the special one because that is the easiest to explain. But if you take this, say this row, then 1 into this 4 into 3 minus 5 into 2, and blah, 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 you will always get the 0. Okay, you will always get the 0. So therefore, if any two rows or any two columns are the same, its determinant is 0. It's another important property. Right, so the next property. If you have a diagonal matrix, remember diagonal matrix means a matrix where all the non-diagonal elements are 0. Something like this, say 1 minus 2, 3, 0, 0, 0, 0, 0, 0. This is a diagonal matrix or triangular matrix. So triangular matrix is where all your maybe upper triangle is 0, all zeros, or lower triangle is all 0. So this is a upper triangular matrix. So it can be upper triangular matrix, lower triangular matrix, or diagonal. Diagonal means all the non-diagonal elements are 0. In all three scenarios, that is upper triangular matrix, lower triangular matrix, or diagonal matrix, its determinant is also its determinant is a multiplication of these diagonal elements. That is 1 into 2 into 6, 12. Just multiply. If they are negative numbers, just use that negative number. That is again very handy because otherwise you start calculating, taking a row or column. But you don't need to do that. If it is a upper triangular matrix, if it is a lower triangular matrix, if it is a diagonal matrix, the determinant is you simply multiply uh, the elements in the diagonal and you will get the determinant. Okay. And of course, you take any row and column and double check. You will always get the same result. Same result as the multiplication of diagonal elements. Okay. That is another very important property. But why? Because if you know this property, when you're supposed to find the diagonal in determinant, you just multiply by the diagonal elements, right? Otherwise, you waste your time. And if it is identity matrix, remember identity matrix is a square matrix where all the diagonal elements are ones, all the non-diagonal elements are zeros. Because it's identity matrix is a special case of a diagonal matrix, still this property is there. So therefore, its determinant is multiplication of diagonal elements. And of course, in this special case where it's an identity matrix, because all are ones, that is by definition of identity matrix, it's going to be 1. So therefore, we can say that identity matrix, for any identity matrix, 2 by 2, 3 by 3, 4 by 4, 5 by 5, its determinant is 1. Right? Remember the word identity is related to 1. So that is another reason why we call this identity matrix. Identity matrix. Right? So matrix where all the non-diagonal elements are 0, diagonal elements are 1, its determinant is also 1. Okay. Right. So now how many properties we discuss? I think we discuss 4 properties. No, 5 properties, right? 5 properties. Right, 6 property. So we have about 5 more properties, okay? Let A be a square matrix of odd n, obviously, otherwise you don't have a determinant. If B is obtained from A by interchanging any two rows or columns, then determinant of B is negative of determinant of A. Say I have a matrix 1, 2, 5. Let's say, let's make it very simple. 1, 2, 3, 4, 5, 6, 7, 8, 9. Say I want to find the determinant of this one. Of course, you can take any row or column and do it. Okay, so you get some number. And if you have another matrix which is obtained by just interchanging two rows or interchanging two columns, any two rows, any two columns. Let's assume I interchange these two columns. So then I get 3, 6, 9, 2, 5, 8, 1, 4, 7. Say I want to find the determinant of this one. And you will find that if this one's determinant is, say, n, this one's determinant is minus n. So if this one's determinant is after calculation minus 5, this will be plus 5. If this is 12, this will be minus 12. Right? So if you obtain a matrix by interchanging any two rows or columns, uh, the resulting matrices determinant is negative times the matrix determinant of the original matrix. Okay. Now let's assume we again interchange two rows of two columns. Now this is, I got it from here to here. So therefore this one's determinant is negative times this one determinant. Now I can do the same thing again. This time I can interchange other two rows or even columns or rows. So let's assume I interchange these two. So then 9, 8, 7, 3, 2, 1, 6, 5, 4. Then what is the determinant of this one? So determinant of this one is negative of this, because from this matrix I have interchanged these two rows. So this is minus n, this is plus, this one's determinant is plus n. So now you can see that these two has the same determinant because we obtain this by interchanging two columns. From this one to this one, we interchange two rows. Of course, these two matrices are quite different, right? You can say 9, 8, 7, right? So by looking at this, you don't know what is 9, 8, 7, right? Because 9, 8, 7 is reverse now. But anyway, so these two have the same determinants because this is the negative and negative of this one is again n. So likewise, if you can see these kind of patterns without calculation, also you can say that, okay, these two are having the same determinant because you can apply this many times, many times. Okay. Right. So that is a very, very important property. Very, very important property. That is why when you, anyway, at the end, we can use these concepts to uh, solve simultaneous equations. So remember, you can write, say, you have 2x plus y minus z equal to 0, say 10. X plus y plus z equal 3. Say x minus 5 plus 3z equal 5. Now you don't care, oh, we can say 1, 2, 3, but you don't care whether this is, say, your second one is the first one is the third one, and so on, right? It doesn't make any change to your solution. Your solution is still solution. So that is also related to this concept because later we are going to look transfer these kind of systems into matrices and then solve it using matrices. So when you transfer, it doesn't matter which one is your first one, right? Which one is your second, right? Just you are working with 3 equations, 5 equations. Anyway, that is also related to this concept, this result. But definitely the sign change, sign change. And again, it doesn't matter, right? You can write 2x plus y minus z, or you can say y plus 2x minus z, y plus x by z, minus y plus x, or you can say is minus z plus 2x plus y, z plus 2x plus y, sorry, z plus x plus y. So it doesn't matter which one is your first element, right? So just as a convention, we write it as x, y, z. Right. So that is the important property. When you interchange two rows or two columns, its determinant is the negative of the original determinants. Next property. Let A be a square matrix of odd n. Obviously, otherwise there's no determinant. If B is obtained from A by multiplying a row. Earlier we discussed multiplying the matrix by a constant. Right? Where is that? Right? Multiply a matrix by constant k. Right? K. That is, you multiply your entire matrix by k, then you can find that it is k to the power n, the determinants of the original one. This time we don't multiply your matrix by constant. We multiply only one row or one column by that constant. One row or one column. Right? Multiply a row or a column by non-zero scalar k. Then the resulting matrix, its determinant is k times, not k to the power n, the determinant of the original one. That is also pretty much common sense. If you think about it, you can prove it yourself, justify yourself. And this is related to the previous rule of k to the power n determinant of A, but that time we multiply the matrix by k. This time we multiply only one row or one column by k. So then it is k to the power determinant of the, sorry, k into determinant of the original matrix. Right? So this is an example just to get a feeling of this rule. Right? So this is my original matrix. Its determinant is 4 to the power 2. Sorry, 4 into 2 is 8. 8 minus 6 is 2. Now you obtain another matrix by multiplying, say this is 2, 2, 3, 4. Okay, so this is actually my original matrix. Let's take this one. Okay, I will take a different example because this example is already there. So I have a matrix, say 3, 1, 3, 4. So what is the determinant of this one? 4 into 3 is 12. 12 minus 3, 9. Now I obtain another matrix by multiplying any row or any column by a constant. So let's say my constant is 5. I multiply this column by 5. So then I have 3, 5. 5 into 1 is 5. 3, I only multiply this column. 5 into 4 is 20. Now what is the determinant of this one? So remember this one minus this one. 20 into 3 is 60 minus 15. And that is 45. And of course 45 is determinant of this one into that constant. That is why I say k times the determinant of the original one. You can see. So this is the original matrix's determinant. This is the new matrix. When I multiply just one column or one row by the constant, that is same as that constant time the determinant of the original matrix. Right? So this is the constant. I multiply a particular row or particular column. And again, if you use your common sense, when you look at this and keep thinking, maybe within 5 minutes you can explain the reason. If you remember the definition of how to find determinant, right? How to find determinant. So again, I'm not going to explain it because I want you to think about it. Of course, if you can't understand, that means still you have not understood what is the definition of determinant is. Because determinant has a very precise definition. According to that definition, definitely this property is correct. This property has to be, right? And previous that k to the power n must also be justified using the same thinking. Right. So I just keep it for you guys. Okay. Right. So the next one. So these properties are very important because when we solve simultaneous equations, we use these properties. We use these properties for advantage. Right. So next property. Let A be a square matrix, obviously, because otherwise there's no determinant. If B is obtained from A by adding a scalar multiple of a row or column of A to another row of A, then its determinant is not going to change. Of course, you get a different matrix, but the two matrices have the same determinant. So what is that? Say this is my matrix, right? Assume. So then what I do is I obtain, right, from this matrix, I take any row or any column and then add a scalar times any row or any other column. And that will replace your original row or original column. So then its determinant is same as original one's determinant. Okay. Is it clear? So let's take an example. So I'll take this example. 114,025,006. Now you get a determinant for this one, some number. Now I obtain another matrix, and then of course we can find the determinant of this one. How do you get this matrix? I will keep two rows or two columns the same, but I'm going to change one row or one column. So in this case, we have decided to keep these two rows same without touching. 025,006. Now what we are going to do is we are going to replace this row by this row plus constant time any other row because we don't take row. For example, I can say row 1 is say row 1 plus 3 row 2. Always this must be row 1 if it is row 1, but this is any constant time any other row. Any constant time any other row. Then you add it. So then we replace this row by this row, this value. For example, I just took 3 as arbitrary value. It can be -2. Right? Right. So let's do like this. So then you need to do it for the corresponding element. So that means for this one will be replaced by 1 plus 3 times row 2 is this one, 0. Of course, 1 plus 0 is 1. And this one, this value plus the same constant, you need to use the same constant for your operation. That is 1 plus 3 times 2. That is 1 plus 6, 7. So then what about this? Row 1, that is 4 plus our constant, we took it as 3, just arbitrary number by 2. 3 times 5, 15. 15 plus 4 is 90. And if you check the determinant of this one and determinant of this one, you will find that the determinant is the same. You just do it as exercise. Calculate the determinant of this one, taking any row or any column. Calculate the determinant of this one, taking any row or column. You will find that the same. Of course, these are two different matrices. Two different matrices, right? Because we did some operation. But the determinant will be the same. Okay? Determinant will be the same. So just do it as exercise. And when you calculate determinant, the easiest thing is take a row or column with lot of zeros. Because then, for example, this into you shade this is anyway 0. This into you shade this anyway 0. Just you need to calculate for this one. When make determinant. It was make it them out when may element බලන්න. දැන් ඔයාලා calculate කරලා බලන්න පුළුවන්. 6 into, so this is 3 1 sorry, yeah, 3 1 3 2 3 3. Right. So that is this, because this is 0, this is 0, this is 6. That is 6 into 3 plus 3 is 6 positive. And then 2 minus 0. 2 minus 0 is 2. So the final answer is 2. මෙයාගේ determinant එකෙන් 12යි කියලා. මෙයාගේ determinant එකෙන් කිව්වේ. Again, I take this one because that is the easiest. Right? So that is 6 into 2 minus 0. The 1 into 2 is 2 minus 0. 2 minus 0 is 2. 6 into 2 is 12. Yeah. So this one's determinant is also 12. This one's determinant is also 12. So of course, these are two different matrices. But when you do this operation, take any row or any column by that column plus constant time any other row or column, you get a new matrix, but the two matrices will have the same determinant. Okay. But when you are doing rows, do it row wise. When you are doing, then you can apply again. So then you are getting different matrices, but all of these matrices have the same determinant. Different matrices, but same determinant. Yeah, those methods are used in solving simultaneous equations. Yes, so that is why we are doing these properties. So all these properties we later use in solving uh, linear equations. Okay, systems of linear equation or calculating inverses and so on. Okay, right. So that is another important property. This is a very important property. Sorry, this is a very important property. Right. So the next one. Now we are into the final property. So now we have discussed up to this point. This is our final property. Uh, if any two columns of a square matrix A, okay, if any row or column of a square matrix A is the sum of two or more elements, then the determinant can be expressed as the sum of the two or more determinants. Okay. So this is very straightforward property. Okay. Sum of any row, any column, right? Say this is my matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, just to make it easy, right? So it's determinant, right? So I want to find the determinant of this one. Now, if I write this as you take any row or column, okay, any row or column. So let's take this column because you can do it for any row or column. Okay, so I'll take this one. So then you write this as just summation of any numbers, positive, negative. But when you simplify it, you must get 2. This one you must get 5. This must be here you must get 8. So it's up to you to decide, right? Anything. But don't after simplifying, you must get the value. I'll write this as something like 1, 4, 7, 3, 6, 9 because I have selected this column for this. Say 2, I will write 1 plus 1. 5, anything, as long as it make 5. Okay. I'll say 7 minus 2. So 7 minus 2 is 5. So 8, I will say 4 and 4. My only objective is make sure you get here. Now I want to find, of course, obviously the determinant of this one is same as this. And now I can break it into two matrices and its determinants and add it. What is this? I will take this column as the first one. These are not changed anyway. 1, 4, 7, 3, 6, 9. But I will take 1, 7, and 4. 1, 7, and 4 here. The second one also 1, 4, 7, 3, 6, 9 is not going to be changed. But now I will take this 1, 2, 4. And if you find the determinant of this one and add it, you will get the determinant of this one. Right? You will get the determinant of this one. So, and again, this can be anything as long as you get these corresponding value, and it can be done for any rows, any columns. Okay. Of course, if you add these two matrices, you will not get this matrix. That is obvious, right? Because then 1 plus 1 will be 2, not 1. I'm not saying that when you add these matrices, you get this matrix. What I'm saying is uh, you find the determinant of these matrices and add it. That is same as the determinant of this one. So don't get misconfused. Right? And it can be, you can do it for any row or any column, and you can break it in whatever the way you want as long as you get these values. Okay. So this is how you write it, but make sure when you break it into A and B, you follow this definition. You take any column or row and break it as multiplication of, right, any two numbers that gives you this. Sorry, not multiplication, summation of any numbers which gives the individual elements, right? This could have been even rather than 4 plus 4, I could have used 7 plus 1 or 10 minus 2. If it is 10 and minus 2, then this is 10, this is minus 2. Okay, right. So those are the properties. මේ property ගැන එච්චරම ඕන වෙන්නේ නැහැ අපිට, but this one is super important. So these properties are super important. This one I told. Last one is not much needed, but anyway, that is also good to know. Right? Any questions? Right. So we'll take a break. After the break, we'll move on to singular and non-singular matrices. So this is all about identity matrix. Sorry. This is all about inverse of a matrix. One of the key concept in matrices is the inverse. Lot of concepts depends on the concept of inverse of a matrix. Okay. So if a matrix has an inverse, we call it non-singular matrix. If a matrix doesn't have an inverse, we call it a singular matrix. That means every matrix doesn't have a inverse. Only some matrices you have inverse. If a matrix has an inverse, it's a non-singular matrix. If a matrix doesn't have an inverse, it's a singular matrix. So first of all, you must know how to check whether is it a singular or non-singular. If it is non-singular, then you need a way to find out what is its inverse. It's something like we have a lot of people uh, in this society. So some are single, some are married or they have partner. So some people they choose to be single. So singular means something like you decided to be single. Non-singular means you have partnership. Partnership. Maybe this guy has a partnership with this. So some are singular, some are non-singular. In matrices, if it is non-singular, you have a unique partner. So this is partnership with this is partnership with. Right? If in matrices, a non-singular matrix has a unique inverse. And this one's inverse is this one inverse is this one. දෙන්නෙක් එක partner වෙන්නේ නැහැ. Not like human society. Okay. And so we'll discuss how to check whether a matrix is singular or non-singular and how to find the inverse after the break. Okay. Right. So now it's 8:05. We'll start at 8:25. Okay, so let's continue. Right, so let's move on to the concept of inverse matrices. Okay, inverse matrices. Uh, Again, the concept of inverse matrix is major concept in matrices, right? So not every matrix has an inverse, but some matrices you have an inverse, right? And if a matrix has an inverse, its inverse is unique, right? So matrix doesn't have more than one inverse, okay? But not every matrix has an inverse also, okay? Right. Uh, so how do you check whether matrix has an inverse or not? Okay, of course, the concept of inverse is only related to square matrices. Okay, the concept of matrix is inverse is only related to square matrices. That means only square matrices we are interested. Okay, right. So the first thing is how do you know whether an inverse matrix has inverse? So simple answer is if its determinant is non-zero, it has inverse. Right? If its determinant is zero, it doesn't have an inverse. So simple as that. Okay, simple as that. So what is the definition of inverse? Say we have square matrix A. If it has an inverse, when you multiply that in matrix by its inverse, you will get identity matrix, right? So if you have square matrix, when you multiply by another matrix, if you get identity matrix, then we say that this is the inverse of this one. And if you cannot find such matrix, or if there's no such matrix, then it is not, it is a non-singular, it's a singular matrix. It doesn't have inverse. Okay. Right. So that is a definition. That is a definition. Okay. Right. So let's take an example. Uh, so then how do you know that whether matrix has inverse or not? Just check the determinant. If it is not zero, it has an inverse, right? For example, this is a 2 by 2 square matrix. Its determinant is 4 minus 6. 4 minus 6 is minus 2. Minus 2 is not zero. That means this one has matrix. This one has inverse. Okay, and we can find it. Of course, if it has an inverse, definitely we can find that. Okay, but finding that inverse is not a I can't say, I would say no, it's not a very difficult task, but it's very little bit boring task. But anyway, we can do it. We can do it. And of course, we can get computers help to do that also once you write a program. Okay. Now, for example, for this one, if you find the inverse, it will be this. How do you know whether it's this is the inverse of this? When you multiply this by this, you will get identity matrix. So let's multiply and see. 1, 2, 3, 4. And how do you know whether check whether this is the inverse of this? You multiply this by this. Okay, this is minus half times this. Okay, so minus half into 4 is minus 2. Minus half into minus 2 is minus so plus 1. This is minus half into minus 3 is minus 3 by 2. Sorry, plus 3 by 2. And this is minus half into 1 is minus half. So let's multiply and see whether we get identity matrix. I will take this row 1 into minus 2, that is minus 2, minus 2, plus 2 into 3 by 2, that is 3. That is first element. So then next element, 1 into 1, 2 into minus half, that is minus 1. So then this element is this row and this column. 3 into minus 2, minus 6. 4 into 3 by 2, that is 2 into 4 into 3 by 2 means this 2 and 2, 2 into 3 is 6. And this element is this and this. 3 into 1, 3. 4 into minus 2, minus 2. And 3 minus 2 is 1. 1 minus 1 is 0. 6 minus 1 is 0. 3 minus 2 is yes, it's identity matrix. So when you multiply this by this, you get identity matrix. So therefore, inverse of this matrix is this. And inverse of this is this, and this inverse of this is this. So that if B is the inverse of A is the inverse of B. Okay. Okay. Right. So first you can check whether it has an inverse by checking the determinant for non-zero. Then of course we can find it. Still, I did not explain. I haven't explained how to find it, but uh, I have explained how to check whether a particular square matrix has an inverse, and also I explained how to check whether uh, particular matrix is the inverse of the other one. So how to check that? You multiply and see whether you get identity matrix. Okay. So this work for any square matrix, 2, 3, 4, 5, 6 square matrices. Right. So now our next task is how to find it. I told you it's a boring task. Right. So there are different ways. In your syllabus, we look at two ways. Two ways. That is, with the help of adjoint matrix, we can find the inverse. Uh, and also there's another approach using the elementary row operations, you can find the inverse. Okay. Both approach you should know. So first we will look at the first approach, which require a little bit of lengthy process. Of course, both approach require a lengthy process, but at the end we get it. Right? Sometimes the issue is of most of the matrices we have inverse matrix, but the inverse matrix can be very ugly. Right? Ugly means with lot decimal places and so on. Right? So maybe your original matrix is like a lot of whole numbers, right? Integers, but maybe your inverse matrix has right a lot of fractions. Right? That is okay. But only thing is it take a little bit of more time, then you simplify. Okay. Now you can see this one also has a bit of fractions. Uh, right. How to find the inverse of a given matrix? First of all, you check whether it has an inverse by calculating the determinant. Say, assume that you have found that yes, it has an inverse. That is, determinant is not zero. Now, how to find the inverse? So of course, first you need to calculate the determinant because determinant is part of the solution. Okay, part of the solution. So this is how you find it, right? So inverse of a matrix, if it is non-singular, is equal to 1 over determinant of A. You know how to calculate determinant, right? Into adjoint matrix of that matrix, right? So if A is a square matrix, and if that matrix is not non-singular, its inverse is 1 over determinant of A into adjoint matrix of A. I will explain what is adjoint matrix of A. Assume this is not equal to 0 because if this is 0, this is singular matrix, no inverse. Okay. Right. You already know how to calculate the determinant. So therefore, now you just need to know how to find the adjoint matrix of a given matrix, given square matrix. Right. So how do you find the adjoint matrix? So adjoint matrix is the transpose of cofactor matrix. So if someone asks what is the adjoint matrix of given square matrix, so the simple answer or initial answer is this is the transpose of uh, cofactor of A. Cofactor of A matrix, its transpose is adjoint matrix. So then you must know how to find the cofactor matrix. So every matrix, you can calculate the cofactor matrix. Every matrix has a cofactor matrix. And every cofactor matrix, of course, we can find the transpose, right? Transpose means rows become columns, columns become rows. So now you must know how to find the cofactor matrix, because then you know how to find the adjoint matrix, which is the transpose. Right. So how do you find the cofactor matrix? So there's a definition for that. Okay. So cofactor matrix of a square matrix is it's another matrix. So if my original matrix we denote as Aij n by n, say my original matrix is Aij n by n by n by n, because we are only interested in square matrices for inverses. So then you can find the cofactor matrix. Let's call it C, which is Cij, again n by n matrix. How do you find this individual element? So Cij means individual element. It can be 1, 1, C1, 1, C1, 2, C1, 3, C2, 1, 2, 2, 2, 3, C3, 1, C3, 2, 3, 3. And Aij is A1, 1, A1, 2, A1, 3, A2, 1, A2, 2, A2, 3. It's matrix. That means this is the a particular general element in C matrix. This is a particular matrix element in A matrix. So let's assume I want to find the cofactor matrix of A. Right? Cofactor matrix is also going to have the same dimension or size, but different elements. Okay. Right. So this is the definition. How do you find this individual element? That is Cij minus 1 to the power I plus j times Mij. Okay. So Mij is you delete the row and column related to Aij and then find the determinant. Right? So it's pretty much like finding the determinant itself. Because in finding the big determinants also we did this. We did this. Okay. So remember when we find the determinant of 4 by 4 matrix and so on, we use the same calculation, right? So we just this and find the determinant. Say when we are interested in this one, we just deleted those and find the determinant of this. So then deleted this and find the determinant of this. The same thing we are doing. Same thing we are doing. Okay. So there also we use the same definition. So that remember the plus minus odd summation is odd negative, summation is even positive. So that is why we have the minus 1 to the power, right? So same definition. Right? So this means if the summation is ij summation is even positive, if I plus j summation is negative, sorry, for odd, it's negative. So this is the mathematical way of telling that, right? Rather than saying when I plus j is even positive, I plus j is odd negative. In mathematical sense, we can say minus 1 to the power I plus j, because this is always either plus 1 or minus 1. Okay. Right. So let's do an example. So let's assume this is my square matrix. Okay. It's a 3 by 3 matrix. Now I want to find the cofactor matrix, because once you find the cofactor matrix, you can find the uh, adjacent matrix. Okay. Because adjacent matrix is a transpose of cofactor matrix. Right. So how do you find the cofactor matrix of a given matrix? So let's assume this is my matrix. Okay. So Cij is minus 1 to the power of this. Okay. So now, say first element. Say I want the cofactor of A, which is again 3 by 3 matrix. Okay. Right. So how to find this? You hide these, because I am interested in this element. You hide this column and row and find the determinant of this, but make sure you multiply by plus 1 or minus 1 depending on the I plus j value. This is basically 1, 1, right? So this is 1, 2, 1, 3, and so on, 2, 1, and so on. So therefore, this is 1 plus 1 is 2, that is even. So therefore, you simplify the determinant of this one and put it there. Okay. Uh, this is 1 into minus 1 is minus 1, minus 1 minus 0 is minus 1. So then you take this this value. So that is you shade this. And this is 2, 1, sorry, 1, 2, which is odd. That means you have to multiply by minus 1 also. Right. So now the determinant of 2 minus 2, 2 minus 1 minus 1. That is minus 2, right? Minus 2 minus minus 2. That is plus 2. That is 0. That's 0. Anyway, this is also 0. So therefore, anyway, it is 0. So next, we will take this element. I told you this is boring task to do, but you need to understand. Right. So then, but make sure you don't multiply by this value. Remember, in calculating determinants, you multiply by this value, but here you don't do that because we are finding the cofactor matrix. Right. So now I shade this, and this is 1, 1, 1, 1, 2, 1, 3. 1, 3 means 3 plus 1, 4. This is positive. So then this is determinant is 2 into 0 is 0, minus minus 1. Minus minus 1 is plus 1. So that is 2 plus 1, 1. Right? 1. But remember, this is 1, 3, which is even. So therefore, it's anyway 1. Because even is you don't need to multiply by minus 1. Okay. Right. So now I need this one. So this is 2, 1. 2, 1. 2, 1 means 3. 3 is negative. Negative. Then you need to hide this negative and find the determinant. 0 into minus 1 is 0. 2 into 0 is 0. 0 minus 0 is 0. So therefore, this is 0. Right? Now you can do it quickly. Then we need to find this. This is 2, 2, 2, 2. 2 plus 2 is 4 positive. Then 1 into minus 1 is minus 1. Minus 2 into minus 1 is minus 2. Minus 2 into minus 1 is plus 2. 2 minus 1 is 1. Okay. Right. So now let's do the next one. This is 2, 3. 3 plus 2 is 5, negative. Then 1 into 0 is 0. 0 into minus 1 is 0. 0 minus 0 is 0. Therefore, it's 0. So let's take this. This is 3, 1. 3 plus 1 is 4. 4 is even, positive. Then determinant. 0 into 2 is 0. Minus 2. 0 minus 2 is minus 2. Minus 2 into positive 1 is minus 2. Right. So the next one. So this is 3, 2. 3 plus 2 is 5, negative. Then 1 into 2 is 2. Minus 2 into 2 is 4. 2 minus 4 is minus 2. Minus 2 into minus 1 is plus 2. And the last one. This is 3, 3. 3 plus 3 is 6. 6 is even, positive. 1 into 1 is 1. Minus 2 into 0 is 0. 1 minus 0 is 1. And this is a cofactor. This is a cofactor matrix of A. Okay. Is it clear? So 2, 1 minus 1. Anyway, this is different matrix, right? 1, 0 minus 1. This is different matrix. So this is the matrix. This is the cofactor matrix of this one. Okay. Right. So now can you now of course if you want to find the inverse of this, you take the transpose of this. That is, rows become columns, and then multiply by the determinant of this, you get the inverse. If you have the inverse, of course, determinant won't be zero. Okay, right. So this is an exercise. Can you quickly prove that uh, this is the cofactor matrix? Taggal karan ba? Taggal karan. Because finding the cofactor matrix is very important. Otherwise, you can't proceed. You just need to prove that this is the cofactor matrix of this. Just you need to do very simple things. Okay. Just remember this is not rocket science at all. Okay, so let's do it. So first one, you shade this. 2 into 1 is 2 minus 0. 2 minus 0 is 2. And this is 1, 1, 1, 1. 1 plus 1 is 2. 2 is even. Therefore, you just write 2 as it is. Okay. Right. Next one, you shade this. 0 into 2 is 0. Minus 1. 0 minus 1 is minus 1. But this is 1, 2. 1 plus 2 is 3. 3 is odd. Minus 1 into minus 1 is plus 1. Okay. So then you take this. 0 into 0 is 0. Minus 1. 0 minus 1 is minus 1. And this is 1, 3. 1 plus 3 is 4. Therefore, you write as it is. So then, of course, this one. 0 into 2 is 0. Minus 1 into 0 is 0. 0 minus 0 is 0. And this is 2, 1. 2 plus, anyway, 0 is 0. Okay. So then this one. 1 into 2 is 2. Minus 1 into 1 is minus 1. Minus into minus 1 is plus 1. That is 3. Then this element is 2, 2. 2 plus 2 is 4 even. Therefore, you write as it is. Now you should be able to do like that. Okay. So that is how you find the cofactor matrix. Okay. It's like determinant, but you don't multiply by a value. Okay. But make sure you have that minus 1 to the power I plus j. Right. So now, if you want to find the adjoint matrix, so that is the transpose. So your first row become first column, second row becomes second column, third row become third column. So that is your adjoint matrix. Now, if you want to find the inverse of this, then it is 1 over determinant of A, this. So now you need to find the determinant of this. That I explained previously, right? මේක දැන් boring කිව්වේ. දැන් ආයෙ අර සෙල්ලම කරන්න වෙනවා. දැන් determinant හොයන්න බෑ. Take any row or any column. Any row or any column. මේ බින්දු තියෙන column එකක් row එකක් හරි ගත්ත ගමන් වැඩේ ලේසි යා. exam එකේදී මතක තියාගන්න. බින්දු වැඩියෙන් තියෙන row එක හරි column එක හරි ගන්න. So I will take this. මොකද හැම කොයි මොන row එක column එක ගත්තත් එකම උත්තරනේ එන්නේ. Right. So then 0 into determinant එක අපි හොයන්න දෙයක් නැහැ. මොකද බින්දුවෙන් වැඩි වෙයි. So then this is remember 2 2 2 2 is even plus 1 into දැන් මෙයා hide කරන්න 1 minus 1 1 2 ඊළඟ එකනත් බිඳුව එන්නේ ඒක ගණන් ගන්න දෙයක් නැහැ දැන් මේක සුළු කරගන්න තියෙන්නේ 1 times 1 into 2 is 2 minus 1 into minus 1 is minus 1 minus minus 1 is plus 1 2 plus 1 is 3 3 into 1 is 3 ඔන්න determinant එක හොයාගත්තා ඒක හඳ මොකද්ද inverse matrix එක 1 over 3 times this 1 over 3 times this because determinant is 3 1 over determinant right so therefore final answer is 1 over 3 times your adjoint matrix so this is the adjoint matrix we got 2 0 1 matrix right simple as that but in case you get your determinant as a 0 right in this case we got a determinant as 3 if you get determinant as 0 then it has no inverse. So therefore, first thing is find the determinant because if the determinant is 0, no point wasting your time finding the adjoint matrix. Simply you can say it's a singular matrix, right? Okay. Right. Any questions? Because now we have finished the basic theory behind matrices. So we discussed some special matrices, what is the determinant of the particular square matrix, and also we discuss what is mean by inverse matrix. Okay, inverse of a matrix and how to find that matrix as well using one approach that is using the adjoint matrix. There's another approach we will discuss later. Okay. Right. So why do we learn these things, matrices? Because matrices have special usage when it comes to solving systems of linear equations. Like linear equations. So in mathematics, when we say linear, so linear means straight line. And linear means not line, straight line. Okay. So that means we have non-linear systems, right? For example, this is a non-linear, right? Y equal x squared something. But if you take something like y equal 2x, y equal 3x plus 5, those are all straight lines, something like this. So if we have, so we can extend it to 3 dimension. So this is 2 dimension, right? In 2 dimension, linear equation is something like this. So you need to understand this, okay? Otherwise you will just memorize it. Say y equal to x plus 5. That is a linear equation because it's a straight line. Say y equal minus 3x plus 5. So maybe it's something like intercept is plus 5. This is minus 3 is negative. That is, so negative means this angle is not small angle, this angle is a big angle. Maybe something like this. We discuss those things in semester 1, straight line, right? Algebra, how to intercept, how to interpret uh, gradient. Gradient positive means something like this. Gradient negative means something like this. Intercept is where it crosses your y-axis. And what is meant by higher gradient? Higher gradient means higher slope, positive or negative. In negative side also, this is lesser slope, this is bigger slope. If this is minus 3, maybe this is minus 5. Okay. So if you don't have square terms or any other higher terms, it's a linear system. But the moment you have x square, x cube, right, it's not a linear system. It's a non-linear system. So that is the first thing you must understand because otherwise these are systems of linear equations. So that is two variable, right? Two, say y equal 3x plus 2. It's a two-dimensional. Remember you have if one dimension, then you can use number line. 2 dimension, we use Cartesian plane. What is mean by Cartesian plane? Having two number lines perpendicular. And usually we call this x independent variable, y dependent variable. And what you get is a straight line if it is a linear system of two variables. And we can extend it to 3 variable, 4 variable, and so on. Right? For example, then we need to introduce another variable, say z. Say z equal 2x plus y. Z equal minus 3x plus 4y. You can have constant also. So x, y, z, then constant. Constant can be 0, x term can be 0, y term can be 0. Like, all three, all are present. For example, in 2 dimension also, you can have y equal x. It's a straight line, right? And if you can have y equal 5. Y equal 5 is a straight line, like this. Always y value is 5. So here also it can be all three terms are there. Sometimes the constant is missing, sometimes y is missing, sometimes x is missing, sometimes even z is missing. So that just like you have x equal 3. Now y is missing, right? So x equal 3 is x is always 3, this straight line. So x equal 3 is also linear equation. But now when you have x, y, z, though 3 variables, it's 3 dimension. It's 3 dimension. Okay. So you need to understand this. Otherwise, you learn matrices like a stupid. Right? So that means you learn matrices to pass exams. pass exams and get a lot of stress. That is you without understanding, learning to pass exams. So that is at the end we have a well-learned person, but highly stressed person. So these guys are not going to serve society, right? But when it comes to three variables, you have the Z axis, X, Y, and then Z, this way or that way. Okay. Let's say this is your Z. So in three dimension, a linear equation, it is something like Z equal to X plus Y minus say plus 5. It's a plane, linear plane. Okay. So linear planes are something like this because the world is three dimension, right? You can't just restrict into two dimension because the reality is three dimension. Civil engineers, mechanical engineers, we need to face reality. The reality is we build three-dimensional things. Okay. Let's see whether we have online tool. Online 3D Cartesian plane graph interactive. So you need to experience it's a බලන්න tool එක මට lazy explain කරන්න. Yeah, 3D calculator, let's see. Yes, right. So remember we just use the 2D calculator in semester 1 and GeoGebra. 2D calculator. මේක කළා දැන් semester 1 වල මම මේක පාවිච්චි කරා හරි. Right. Y equal x line. Right. මම කොහොමද මේක experiment කරන්නේ y equal x plus 2 or x plus 3. You can see parallel to y equal x line, but intersection is 3. So then say so this y equal x, this is y equal මේක කළා ඒ කාර්ය කරපු කට්ටියට මේ හරි ලේසි දැන්. ඒගොල්ලෝ වැඩක් අවබෝධයක් ඇතුව කරන කට්ටිය. This is 2x higher gradient. Say this is y equal minus x, which is perpendicular to y equal x line. Minus 6. Then our formula making an y equal minus x plus 5 here. Y equal minus x plus 5 is parallel to y equal minus x, but its intersection is 5. So therefore it will go like this. අපි ස්කෙචින් කරා එදා ක්ලාස් වල semester 1 වල කරේ මේවට මේක තමයි ඉගෙන ගන්න ඕන ක්‍රමය. So it will be parallel to this and like this. Okay. අඳින්න දෙයක් නැහැ. අඳින්න කලින් දැනගෙන ඉන්නවා. Say y equal minus x plus 5. So y equal minus x plus 5 plus 5. Well, this one parallel to this one, but cross set minus plus 5. Okay. So likewise, you should have idea about these things. What is mean by parallel? What is mean by perpendicular? What is mean by same intercept? What is mean by same gradient? Same gradient means parallel. Same intercept means cross the y-axis at the same time. What is mean by negative gradient? Positive gradient? What is mean by higher gradient like x versus 2x? Right? X versus half x. So then you get your confidence. Right. So now you must extend that confidence to 3 dimension. Right. For example, if I write y equal 1, still I can write on Talyati. So this now here, this is x, and this is y. So y is always 1 because this is y equal 1. You can see this down also it is there, but you can't see. Okay. Uh, any coordinate, three-dimensional coordinate in this plane is y equal 1. Any of these coordinates. Because you can't run away from three dimension because we live in three dimension, right? So engineers, doctors, we face the reality. වා ත්‍රී ඩයිමෙන්ෂනින් පලා යනවා කියන්නේ දොස්තර කෙනෙක් කියලා ඇක්සිඩන්ට් එකක් වෙලා එන මිනිස්සෙක් කකුල තුනට හතරට කැඩෙනකොට ඔයා ගෙදර දුවනවා. ඒතර දොස්තරකම කරන්න බෑනේ. මෙඩිකල් කොලෙජ් එකකින් ඩිග්‍රියක් ගත්තට. නේද? හાર્ට් ඇටැක් එකක් ඇතිලා මිනිස්සෙක් කෙනෙකුට බාගෙට පණ ගිහලා ඔයා ගෙදර දුවනවා. නැත්නම් මිනිස්සයා මැරිච්ච ගමන් ඔයා ගෙදර දුවනවා. බුදුහාමුදුරුවෝ මලමිනියක් කියලා. ඒතර ડોක්ටර් දොස්තර වැඩේ කරන්න බෑනේ. ඒ නැත්නම් නොකර ඉන්නවා. දොස්තරකමක්. ත්‍රී ඩයිමෙන්ෂන් උනා පැනලා දුවනවා නම් මැත්ස් ඉගෙන ගන්න එපා. හරි විශේෂයෙන් සිවිල් මෙකැනිකල් වගේ ඉංජිනේරින් කරන්න එපා. මෙතන අපි කරන්නේ ඒ වගේ ඔයාලට පුළුවන් දැන් උදාහරණ 3 dimensional modeling කරන්න වෙනවනේ අපිට සමහරවිට කම්පියුටරේ. Right? Right. So this is the easiest to understand, right? Just one variable but three dimension because we are interested in other variables. Okay. So what about something like uh, Z equal 3? Then what පුළුවන් වෙනවටක් ගන්න. Because this is the Z. Okay, I'll hide this. So this is the plane. If Z equal -3, right? -3. Then what? යට ඉන්නේ. යට ඉන්නේ. කරකොල බලන්න පුළුවන් ආඩ හරි. දැක්කද යට ඉන්නේ. Z equal -3. Now you should be able to extend it to something like, say, Z equal x, Z equal x plus y. These are all linear systems. තල හැබැයි flat තල. flat තල. ඒ තලේ නිකන් ඍජු කෝණාශ්‍රයක්. හැබැයි ඉන්නේ අවකාශය. So what we are interested is this kind of equations. So these are all what? Linear systems. Yes, three dimension. You have three variables, but no square terms, cubic terms, and so on. Right? No square, no cubic. So these are linear systems. So similarly, we can think about non-linear system like y equal x squared, but now this time it is two dimension. Okay, sorry, three dimension. You can see. අර පරාවලේ වගේ හැබැයි මේක 3 dimension පරාවලයක්. අපි ඔක අනිත් එකක් ගත්තනම් තවත් බේසික් ඔක එක්ස්ප්ලেইন කරන්න. say Z equal Z equal x squared. Yeah. කරබෝල බලන්න. And මෙහෙම බලමු හොඳට පේන්නේ. Z equal x squared. Okay. So this is x, this is Z. දැන් මම y එක වලට පේන්නේ නැහැ. y එක තියෙන කෙලිම ආගේ ඉස්සරහට ඇවිල්ලා තියෙන y. හරි ඒක වලට පේන්නේ නැත්තේ හරි. පොඩ්ඩක් ඇද කරාම පේනවනේ y එක. Right. So this is not a linear system. This is not a linear system, right? So for example, I can say x squared plus 1 plus 2. එමෙයා දෙකකින් ඉස්සෙන්නවා. එකක් උඩට ගියා. කලින් බිඳුවෙන් එක ඇවිල්ලානේ. So these are non-linear systems. So, right? So what matrices, in matrices, what we are interested is linear systems, right? Not this kind of a system. It's like y equal, say, Z equal x plus y. Right? So this is linear system. තලයක්. සමතලයක්. සමතලයක්. Then what about Z equal x plus y plus 2? තලේ පොඩ්ඩයි හරි උඩට පැන්න. Right? These are the linear systems. Okay, so when it comes to this kind of linear systems, right? So then there are interesting things. What about if you have two linear systems like z equal x plus y plus 2, then z equal say 2x plus 3. So now we have two linear systems. Sorry, two linear equations, right? So this red one and this sort of a blue one. අපි එකට වෙන කලර් එකක් දාමු. Say red one and this blue one. Okay. Colors මාරු කරන්න දෙන්නේ නැද්ද මට? ඔයා log වෙන්න කියනවා හරි. වෙන කලර් එක බාර ගන්න නැත්නම් log වෙන්න. නෑ පුළුවන් නේ. Now you can see two linear systems. Now when you simultaneously solve this kind of system, what you get is set of answers like this cross section. In two dimension, when you simultaneously solve equations, you get this kind of cross sections, xy values, right? So in two dimension, what you get is two straight lines, right? Two straight lines like this and like this, and your xy value is this. But here in three dimension, you get sometimes not just one point, set of points. Like all these are answers, solutions. But there are rare situations we have three dimension, just one answer is there. Let me explain it using a document. First of all, you need to understand. Then, of course, doing the calculation is not the difficulty. Let me search. Three variable, one solution, many solution, linear systems. Let me go into another one. Like something like this. This is a very good example. Now this is three dimension. That means three variable system. That is why we have three dimensional graphs. Okay. Three dimensional graph. So where are the other? Yeah. So these are three equations, but you can see these are parallel. These three planes are parallel. So that means this one has no solution. This one has no solution. Why? A solution means intersection points. Intersections of these three planes. But when the planes are parallel, there are no intersections. It's same as when two linear equations, right? So there are no solutions for these two, right? Because no intersection points. This is two dimension, this is three dimension. And in two dimensions, if we have something like this, we have one solution, xy pair, just one solution. Okay. So there are situations in 3 dimension also, and we can extend it to 4 dimension also, or any dimension. Now you can see that. Look at the 3 planes. Red plane is there. This green plane is there. This sort of a indigo plane is there, and all 3 planes cross all 3 planes, right? For example, here the 2 planes are intersecting. Here the indigo and red plane is intersecting, but not the green one. Here indigo and green is intersecting, but not red one. But you can see there's one point here where all 3 planes intersect. All three. Your green one is also part of this point, indigo, red. So this kind of a situation, we say we have one solution, unique solution, because we get after say 2x plus y equal plus 3 is say uh, z plus 2y plus x equal 5. 2z minus 2y minus x equal 3. uh, z plus y plus x equal 5. Then when you simultaneously solve this, you get just one answer saying x equal this, y equal this, z equal this. So this kind of situation, we say that we have one solution or unique solution. That means you just get x, y, z values. But earlier, no solution. Why? There is no single point that all 3 planes intersect. And there's another possibility like this. So now you can see there are 3 planes or 3 linear systems. But now all of these points, you have all 3 intersect. This plane, and this plane. Now you can see in this line, all 3 planes are getting intersected. So this is a special case where we say we have infinite number of solutions. Okay. It's like you have the 2 straight lines, but the 2 straight lines are the same. So then any point is satisfying both. Actually, both, there's nothing called both actually. The 2 lines are the same. But here it's not very interesting in 2 dimension, but 3 dimension it's interesting because you can have 3 planes having infinite point intersections. All three meet at the same point in infinite positions, straight line. So therefore, what are the 3 possibilities? Infinite number of solutions for the systems of linear equations. Unique solution like this, where only one XYZ pair will satisfy all 3, and no solution. So that means when we simplify, solve 3 dimensional systems or higher, there are 3 possibilities: unique solution, 2 solutions, uh, infinite number of solutions. Okay, infinite number of solutions. So that is the first thing you need to understand. So then, if there's a unique solution, how to find it? If there are infinite number of solutions, how to find it? And how to check whether there are no solutions? So that is what we are going to do now. Okay, that is our next task. Is it clear? Right. So now we want to remember our task is make it abstract, make it generalized so that you understand abstract thinking. So rather than be strict into 3 variables, because in O level you just strict with 2 variables. 2 variables means 1 dimension. So 3 variable means 3 dimension. 4 variables means 4 dimension. So what is the fourth dimension? So there's no clear definition of what is the fourth. 1 dimension you can feed. 2 dimension you can feed. 3 dimension also you can feed because you are a 3D person. But the moment you say 4 dimension, sometimes you get little bit uncomfortable because you are a 3 dimensional object. This world is 3 dimensional. But we can extend as because our imagination is there, right? So that is one of the great asset humans have. So we can extend it to fourth dimension, fifth dimension, sixth dimension. That is how people like Einstein came up with these theories. Because so yes, we say that these guys are genius, but only thing is these guys uh, they break barriers. So yes, world is three dimension. So but they got think of what about the fourth dimension, fifth dimension? Right? What are the possible usages? So a lot of people consider the fourth dimension as time. Okay, but you can think of something else also. So then what about the fifth dimension, sixth dimension? Right? Can we think of like that? And if so, how do you find solutions to those kind of systems? So therefore, we generalize it to n dimension. So n unknowns means n dimension, right? And we have m number of linear equations. So we have m number of equations, 1, 2, 3, m, and n unknowns, x1, x2, xn, because you can't say xy z, right? When you want to generalize, right? So therefore, rather than x, y, z, we just say x1, x2, xn. Basically, x1 is a variable. Say you can think x1 is x, x2 is y, x3 is z, but we generalize it to xn. So that means n unknowns, m equations. And here y1, y2, ym is just a constant. Remember, we can write y plus 2x equal 3. So don't think that y is a variable, right? Here we just use y as a constant. Or you can say C1, C2, Cm. Okay. And this kind of a system is called a general linear equation or system of linear equations. Okay. So we have M relationships, N unknowns. Okay. And you can put it into a matrix format also. So that system, that is your coefficients. So these are the coefficients. For example, say 2y plus x equal 3, uh, y minus 3x equal to, of course, this is two-dimensional. Okay. Remember, two-dimension is a special case of this. So then you can put it into matrix format. 2, 1, 1 minus 3. This is minus 3, this is 1, this is 2, this is 1, into, in our case, of course, it's y and x equal, because this is the first variable, this is the second variable, equal 3, 2. So you can represent this linear system using this. Why? Because when you multiply 2, 2y plus x, remember 2y plus x, right? Which if you multiply this matrix multiplication, this is 2 by 2 matrix, this is 2 by 1 matrix, you can multiply because these are the same. So then multiply 2 into y plus 1 into x, 2y plus 6. This is my first element. Remember what you get is 2 by 1 matrix. 2 by 1 matrix equal, of course, this you have 3 and 2. This is my first element. Second element is this row by this column, right? That is y minus 3x. Y minus 3x. Now we have the two matrices. If two matrices are the same, individual element must be the same. So then 2y plus x must be 3. Y minus 3x equal to, yes. So that means this represent this. මොකද මම මේක සුළු කරාට පස්සේ මේක එනවා. මේ matrix එක සමාන නැහැ, element සමාන. So therefore we can represent a linear system using this kind of a matrix arrangement. And when you have this kind of matrix arrangement, this represent this linear system, and we can extend it to 3 dimension, 4 dimension, or n dimension. Okay. So therefore, this is the matrix representation of this kind of a linear system. Okay, this kind of a linear system. And we can, for simplicity, short, we can write it like AX equal Y. Okay, so A is the matrix of coefficient. Coefficients are these values. Sangunak kiyanne matrix of coefficient into X. X is the representation of n by 1 uh, column matrix, where x1, x2 to xn are variables, like x, y, z. And this is your constants. Constants. So A is the coefficient matrix, X is your column matrix representing variables, Y is a column matrix. Column matrix and one column matrix representing your constants. Okay. And if Y is zero means all are zeros. All are zeros. So that means you don't have constant terms. If you don't have constant term in any of the linear equation, that means you have these xy terms, but no constant. So that means all are zeros. So then we say it's a homogeneous system. It's a special case. For example, 2y plus x equals 0, x minus y equals 0. This is a homogeneous system because this matrix is a column matrix having all 0 or 0 column matrix. Okay, so it's just a special case. But in general, these can have enough values. Okay. Okay. Right. As I told you, there are three possibilities when you have this kind of a linear system. What are the three possibilities? No solutions, like the parallel planes. Infinite many solutions, one solution. So remember that you just need to understand. No solutions, unique solution or one solution, infinite number of solutions. Infinite වෙන්න පුළුවන් ගොඩක් විදි තියෙනවා මේ තල තුන කැපෙනවා. තල තුන කැපෙන නිසා අර රේඛාවක. Point එක නෙමෙයි. Okay, so these are the three possibilities. Unique solution, infinitely many solutions, or no solutions. If you have solution, either unique or infinite, we say it is consistent. Consistent. So that means if there exists a solution which satisfy all the equations, it can be one solution, no infinite solutions. So then we say it's consistent system. But if you have no solution, that is called inconsistent linear equation system. Right? That is none of the solution is there. That means those එම parallel වෙන්න ඕනෙත් නැහැ හැබැයි යා. දැන් හිතන්න පුළුවන් මේ parallel වෙන්න ඕනද කියලා. parallel වෙන්නේ නැහැ. තල තුන තියෙනවා. තල තුන හැබැයි කොයි වෙලාවවත් එකට කැපෙන්නේ නැහැ. දැන් එහෙම example එකක් තමයි මෙන්න මේක. නේද? So there are three planes and three planes intersect. ඔය three planes වලින් දෙකක් intersect වෙනවා. වෙන වෙන හැබැයි තුනම එක තැනක කොහෙවත් එකට intersect වෙන්නේ. So then also infinite then also no solution. No solution වෙන්නේ parallel වෙන්න ඕනේ නැහැ. Right? තල තුන ඔහේ තියෙනවා. තල තුන දෙක දෙකක් කැපෙනවා. හැබැයි තුනම එකට කැපෙන්නේ නැහැ. එක පොයින්ට් එකකට කැපෙන්නේ නැහැ. ලයින් එකකට කැපෙන්නේ. එහෙම ඔයාලට හිතන්න පුළුවන් තරම් හරි. මෙහෙම 3 dimension එක ගත්තාම මේ තලයේ මෙහෙන් යනවා. මේ තලයේ මෙහෙම යනවා. මේ තලයේ මෙහෙම යනවා. ඒක තල තුනම එකට කැපෙන්නේ නැහැ. තල තුනම එකට කැපෙන්නේ නැහැ. හරි දේසියා. එතකොට that is also no solution. No solution means inconsistent. Unique solution, no infinite many solution means consistent. Okay. And if a system is homogeneous means all these values are zero, right? Homogeneous, then it can't be inconsistent. Without inconsistent mean because at least one solution is there. Okay. If a homogeneous system has unique solution, that is a trivial solution. Trivial solution can x equals 0, y equals 0, z equals 0 solution. If x1 equals 0, x2 is equals 0, is x3 equals 0, 0. ඒක හරිය තියෙනවා අනිවාර්යයෙන්. Homogeneous නම්. Okay. Now these are some examples. This is a two-dimensional where you have unique solution. Right? So these are three-dimensional example where you have infinite many solutions. Okay. And this is example of three dimension where you have no solution. Right? Then make a solution now. Therefore, this one has infinite many solutions. So this one has unique solution of positive two dimension. Okay. දැන් කොහොමද මේක හොයන්නේ කියන එකයි ඊළඟ වැඩේ. So there are techniques of solving this kind of linear systems. So in your syllabus, you have two approaches, elimination method and so that is one approach. So the next approach is yeah, both are called elimination methods, but we use slightly two different techniques. Okay, slightly two different techniques. Right. So now you go through your note because this is not your note. This is basically all syllabus note. තාම ඉවර නෑ හොඳේ. ටොපික් එක. තව ගොඩක් කරන්න තියෙනවා. තාම solve කරන විදිය කිව්වෙත් නෑ. Right. But now if you go through your note, now lot of ground is now covered. තාම මේ හරිය දැන් කතන්දර ටිකක් කියලා තියෙන්නේ මේ මොකද්ද one solution many solution. ඔයාගේ නෝට් එක පටන් ගන්න එතනින්. අපි එතනට ආවේ ගොඩක් පහුවෙලා. Okay. So no solution. Infinitely many solutions. Right. මේ සමහර ඒවා අපි තාම කරේ නැහැ. ඔයාගේ නෝට් එක තියෙන්නේම නිකන් නොතේරෙන භාෂාවක්. හරි. මේ වෙක්ටර්ස් තාම කරේත් නැහැ. ඔයා පටන් ගන්නෙම මේකෙන් තමයි. ඒක මේක දැක්ක ගමන් ස්ටුඩන්ට් බය වෙනවා. මොකක්ද යකෝ මේ මගුලක් තියන්නේ. මේ පළවෙනි නෝට් එකේ තියෙන්නේ. මේක තමයි පටන් ගන්න ඕනේ. නෝට් මොකද එතනට ආවේ නැහැ තාම හරියට. මේ දෙවෙනි නෝට් එකේ තියෙනවා දැන් ගොඩක් කරලා තියෙන්නේ. නෑ වෙක්ටර් ස්පේස් උත් තාම කරේ නෑ. So there is 1.6 නේ. 1.2 මේ ටික කරලා තියෙන දැන් ගොඩක් හැබැයි තාමත් කරේ නෑ මේ හොයන විදිය. හරි හොයන විදිය කරේ නෑ. ඇත්තටම ආගේ නෝට් එක හදලා තියෙන්නේ කන පිටට. අගින් ඉඳලා මුලට එන්නේ. හරි. අගින් ඉඳලා මුලට එන්න හදලා තියෙන්නේ මම දන්නේ ඇයි එහෙම හදලා තියෙන්නේ මට අමාරු වෙන හේතුවක් දන්නේ නැහැ. So 1.4 ඒ වරන්නේ මේකේ සමහර ඒවා දැන් කරලා තියෙන්නේ. සමහර ඒවා කරලා නැහැ තාම. Right. So this is 1.4. මේව තාම රෝ රෑන්ක් එහෙම කරේ නැහැ. Right. So then 1.5 මේ වටින් කරලා ඉවරයි. දැක්කද 1.5 ටික තමයි අපි කරලා තියෙන්නේ. Right. 1.5 determinants how to calculate මේ ඔක්කොම කරලා තියෙන්නේ. 1.5 එක තනි කරම කරලා තියෙන්නේ. Properties of determinants දැන් අද කතා කරේ. මේ ඔක්කොම කරලා තියෙන්නේ. Right. Adjoint matrix. ඒවත් වෙනවා වාගේ නෝට් එක හදලා තියෙන නිකන් කන පිටට කියලා. හරි. මම දැන් ඇයි එහෙම හදලා තියෙන්නේ කියලා. හරි. So that is 1.5. Then 1.6. 1.6 සම කරේ නෑ. මේවා තමයි මම highly abstract topic කියලා. හරි. So these are extremely abstract topics. Then 1.7 we have not done. So these are the extremely abstract. දැන් මේ තාම කරන්නේ නිකන් පොඩි කතන්දර ටිකක් කරන්නේ. ඇත්තට මේවා ඉතා abstract. හරි මේවා explain කරන්නත් පිස්සු හැදෙනවා. හරි. explain කරන්නත් ඉතා අමාරු කතන්දර තියෙන්නේ. නමුත් මේවයින් නෙමෙයි exam එකේ question අහන්නේ. question අහන්නේ මම දැන් ඔය කරන ඒවායින්. හරි. කරන ඒවායින් තමයි exam එකේ questions ටික අහන්නේ. ඊට පස්සේ 1.8 ඔව් මේවයින් එච්චර ප්‍රශ්න ඇත්තටම අහන්නෙම නැත්තරම් දැන් මොන කනෙක්ට් කරනවා ඒගොල්ලෝ වෙක්ටර්ස් සහ මේට්‍රිසස් කියන දෙක. ඒතකොට ඊට කලින් අපිට වෙක්ටර්ස් කරලා ඉන්නවා. හරි. because this is vector. But anyway it's good to know at least මේවා නිකන් තල වශයෙන් හරි තේරෙනවනේ ඒ වගේ. අපි කියන්නේ මීටරේ කියලා. මීටරේ හොඳ වෙනවා. හරි මීටරෙන් තමයි අන්තිමට ගේම ගහන්නේ ජීවිතේ. ජීවිතේ ජීවත් වෙන්නේ විශේෂයෙන්ම ඉංජිනේර්ස්ලා ප්‍රොෆෙෂන් එක කරන්නේ මීටරේ. ඔයගොල්ලෝ දන්නවද දන්නේ නැහැ. IT ෆීල්ඩ් එකට දැන් මම උදාහරණයකට මම IT නෙමෙයි කරේ. හරි මම IT කරලා නෙමෙයි මම කරේ ඉංජිනේරින් ඩිග්‍රිය. නමුත් අපිව IT ඩිග්‍රී ගත්ත ඒ කාලේ ඇත්තටම වැඩි IT තියුනේ නැහැ. කම්පියුටර් සයන්ස් තියුනේ නැහැ. ඒත් අපිව ජොබ් වලට ගත්ත ටක් 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 ගාලා. ඒකට අදටත් ගන්නවා. අදටත් මම දන්න ගොඩක් අය ඉන්නවා. මොරටුව කැම්පස් එකට ගිහලා ඉලෙක්ට්‍රිකල් ඉංජිනේරින් කරනවා. මමම කියලා තියෙන අනන්තය. උඹ ඉලෙක්ට්‍රිකල් ඉංජිනේරින් කරන්න එපා කම්පියුටර් සයන්ස් කරපියේ. හරි. ඔය න්යායෝන්ගේම ළමයි ඉන්නවනේ. නෑ 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 මම ඉලෙක්ට්‍රිකල් ඉංජිනේරින් වලට ආසයි. වැඩි ලකුණු ගන්න නෑ ඉලෙක්ට්‍රිකල් ඉංජිනේරින් කරන්න. ඒක කරනවා. ඊට පස්සේ ඔන්න කිව්වනාගෙන හන්දා කරනවා. ඊට පස්සේ ජොබ් වලට යන්න ගියාම ජොබ් නෑ ලංකාවේ ඉලෙක්ට්‍රිකල් ඉංජිනේර්ස් වල. හරි ජොබ් නෑ. ඒතකොට ඔන්න ආයේ වැඩට යනවා. කොහෙද? IT ෆීල්ඩ් එකේ. software development field. software engineers field. හොඳ පටි ගන්න. හරි. හරි. මේගොල්ලෝ මේ සෑහෙන පිරිසක් ඉන්නව නේද? ඉලෙක්ට්‍රිකල් ඉංජිනේරින් කරලා, ඉලෙක්ට්‍රොනික ඉංජිනේරින් කරලා, සමහරලාට සිවිල් කරලා IT යන. ඇයි ඒ ගන්නෙ? මීටරේ හොඳා. මීටරේ හොඳා. ඒකනේ ආ ඉංජිනේරින් කරේ. ඒත් ඉංජිනේරින් කරනකොට ඉංජිනේරින් මැත්ස් ඉස් හරි ඔයගොල්ලෝ මැත්ස් සිලබස් එක අරන් බැලුවොත් එහෙම තනිකර 3 dimensional maths උගන්වන හොඳටම. හරි. ඉංජිනේරින් මැත්ස් සිලබස් එකක් ගත්තොත් එහෙම මොකද එතන ඉන්නේ A level maths කරපයින් ඒ University of Morocco වගේ තමයි. ඉංජිනේරින් සිලබස් ඕගොල්ලන්ට කරන්නේවට වඩා පද ලෙවල් එකට යනවා. එතකටින් කරන්නේ ඒගොල්ලෝ බය නැති කරනවා. බය නැති කරනවා වගේ මේ ප්‍රැක්ටිකල් යූසේජස් තියෙනවා ඒගොල්ලන්ට වැඩි. මම මේ කරන්නේ මැත්ස් ඉගෙන ගන්න එකේ තියෙන වටිනාකම. හරි. ඒගොල්ලන්ට ටක් කරලා ජොබ් දෙන්නේ ඇයි ඒ? මීටරේ ගන්නවා. ඒගොල්ලෝ පොඩි පොඩි ප්‍රෝග්‍රෑමින් පොඩි නෙමෙයි සාමාන්‍ය Java C වගේ ඒවා ටිකක් Java නම් වැඩි කරන්නේ. ඒගොල්ලෝ C එහෙම උගන්වනවා. මම මේ කියන්නේ ඉලෙක්ට්‍රිකල් එහෙම කරන්නේ නැහැ. Javaත් මම හිතන්නේ කරනවා. ඔව් Javaත් ෆස්ට් ඉයර් කරනවා. ඩවුන්ලෝඩ් කරන්නේ. I think this is computer science නෑ. I think මේ mathematics. This is anyway computer science and engineering. මේ දිකට maths උගන්වන්නේ නැහැ. මෙතන mathematics. මේ ඇවිල්ලා fluid mathematics එහෙම ඒගොල්ලන්ට උගන්වනවා. හරි. computer science කරන්න ගියත් ඒගොල්ලන්ට අනිත් ඒවා උගන්වනවා. හරි. දිගින් දිගට maths තියෙනවා. දිගින් දිගට maths තියෙනවා. හරි. මේවා highly technical. Right? Intelligent systems, image processing. Image processing is heavily vectors. Image processing is all about vectors. Okay? All about vectors. ඔයගොල්ලෝ මෙච්චර සබ්ජෙක්ට් ඉගෙන ගන්න නැහැ හරි. ඒගොල්ලන් ගොඩක් සබ්ජෙක්ට් තියෙනවා සිලෙක්ට් කරන්න. So therefore don't think that this is difficult. මේ level එකට හිතන්න වෙනවා ඕගොල්ලන්ට. හරි. මේ level එකට කියලා හිතන්න වෙනවා. So then it increase your confidence, okay? Right, so we'll stop at this point. So the next class we will discuss how to solve these linear equation systems, especially think three dimension, right? What is the meaning of no solution? What is the meaning of infinite solutions? So you get rid of this two-dimensional mentality and start thinking three-dimensional because we live in three-dimensional world. Right? We live in three-dimensional world. And also, if possible, start self-learning calculus because Calculus is not in your syllabus. Right? Say, say math is fun. Calculus. ගිහිල්ලා ඉවර මොකද්ද limit එකක් කියන්නේ? කියලා දැන් ඉගෙන ගන්න. මොකද I'm not going to do those. Okay. So what is a limit? Right? What is differentiation? නැත්නම් මේ අවකලනය කරනවා කියන්නේ මොකද්ද? d by dx කියන්නේ මොකද්ද? හරි. දැන් ඒවා ඉගෙන ගන්නවාට බය නැති කරගෙන යන්නේ මේ ටික ටික. හරි. මොකද්ද මේ slope එක කියන්නේ? ඊට පස්සේ what is integration? Right? Where is integration? ඉන්ටිග්‍රේෂන් කරනවා කියන්නේ මොකද්ද? අනුකලනය කරනවා කියන්නේ. මේ අනුකලනය කරාම වෙන්නේ වර්ගඵලය. අපි ඕන graph එක අනුකලනය කරන වර්ගඵලය ගන්න. අපිට මොකක් හරි මේව graph එකක් තියෙනවා නේද? It can be anything. Right? ඔන්න මොන හරි දිනකට y equal 3x squared plus 2x sorry sorry y equal 3x cubic plus 2x squared minus 3x plus 5 කියලා. මට අනුකලනය කරන්න කියනවා මෙහෙම මේ සමීකරණය දීලා 3x cubic blah 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 dx say 0 to 5. එතකොට වට එනවා මෙන්න මේ වර්ගඵලය. දැන් අනුකලනය කරන විදියක් තියෙනවා. මොකද්ද මේ අනුකලනය කරනවා කියන්නේ? හරි? So you need to understand. වඩා මේ තේරුම් ගන්න පුළුවන්. අනිත් පැත්ත තේරුම් ගන්න පුළුවන්. ඔයගොල්ලෝ තේරුම් ගන්න බැරි කමක් නැහැ. ඔයගොල්ලෝ මිනිස්සුනේ. ටික ටික තේරුම් ගන්න මොකද්ද මේක ඩෙෆිනිෂන් එකක් තියෙනවා මේක මේ චූටි කොටස් ඍජු කොටස් වලට කඩලා තමයි අපි මේක හදලා ඊට පස්සේ ඒක චුට්ට චුට්ට ඍජු කොටස් චූටි චූටි කරගෙන යනවා ඒතර චූටි චූටි කරන්න තියෙන එරර් එක නැති වෙලා යනවා හරි ඒකයි මේ පෙන්නනේ එරර් එක නැති වෙලා යනවා කියලා ටික ටික හරි මේ මෙතන පොඩි එරර්ස් තියෙනවා ඍජු කොටස් එකක් කියලා ගන්න බෑනේ මේක ඍජු කොටස් එකක් නෙමෙයිනේ මේ වර්ගඵලය වෙනකොට ගන්න මේ වර්ගඵලය හැබැයි මේ වර්ගඵලය අරගෙන ඉවල ඊට පස්සේ කරනවා මේවා පොඩි පොඩි කෑලි චූටි චූටි කරන එක තමයි ඩෙල්ටා x කියලා concept එකක් තියෙන ඉන්ෆිනිටෙස්ටිමල්. ලොකු පොඩි වෙන්න මේ එරේ එක නැති වෙලා යනවා. එරේ එක නැති වෙලා ගිහලා අනුකලනය කරනකොට perfect answer එකක් බවට පත් වෙනවා. What you get is a perfect answer at the end. Okay? පේනවා. දැන් චූටි මෙතන තියච්ච මේක දැන් පොඩි කරලා දෙන්න. පොඩි කරනකොට මේ එරේ එක සමහර මේ එරේ එක පොසිටිව් නෙගටිව් හරි. චූටි කරන්න මේ එරේ එක කැපිලා ගිහිල්ලා පේනවා. මේ එරේ එක නැත්තරම නැති වෙලා යනවා. මේකයි මේ සැරින් සැරේ පෙන්නන්නේ ආ. ඒ දෙක නැති වෙනවා කියලා. So likewise, so you should be able to understand මේ වන A level වලට ගන්නවා හරි. A level maths වලට. Right. So we'll stop at this point, right? Thank you.